Hi friends, in our former classes we have studied about haloalkanes. In this session, which is 7th session, we shall study about haloarenes. This forms the second part of the chapter haloalkanes and haloarenes. So today we shall study haloarenes. We know what haloalkanes are. They are the alkanes in which one or more hydrogen atoms were replaced by halogens. They are the halogen derivatives of alkanes, whereas haloarenes are halogen derivatives of aromatic hydrocarbons. In the word haloarenes, halo stands for halogen and arene stands for aromatic hydrocarbons. Aromatic hydrocarbons. Therefore, haloarenes are the organic compounds in which one or more hydrogen atoms of the aromatic hydrocarbons are replaced by halogens. Like example, this is an example of benzene. In benzene there are 6 hydrogen atoms on all the 6 carbon atoms. So if one hydrogen atom is replaced by any one halogen, we call this as a haloarene. This is example for chlorobenzene, or else this is toluene. In toluene, if one hydrogen atom in any place is replaced by any halogen, say bromine, then this is an example of haloarene. So what are haloarenes? Haloarenes are the organic compounds in which one or more hydrogen atoms of aromatic hydrocarbons are replaced by halogen atoms. Haloarenes are otherwise called aryl halides. This is same like haloalkanes. Haloalkanes are otherwise called alkyl halides. Haloarenes are otherwise called aryl halides. Haloalkanes had the general formula Rx. Aryl halides are generally represented as ARX. In most of the books you will not be finding this formula ARX. It is for our convenience that we represent haloarenes as ARX. Let us see their nomenclature. The nomenclature of haloarenes is quite simpler. In common naming system, haloarenes are called aryl halides, and aryl halides in IUPAC system are called haloarenes. For that reason, if I have this example of chlorobenzene, then its common name is aryl halide, means phenyl. Benzene does not become benzyl. Just as methane becomes methyl, ethane becomes ethyl, benzene does not become benzyl, it becomes phenyl. So phenyl chloride is common name, whereas its IUPAC name is chlorobenzene. It is chlorobenzene. If I have here Br, then it becomes phenyl bromide and bromobenzene. These names are same for all the halogen substituted derivatives of benzene. If there are di-substituted benzene compounds, like this example, if there are di-substituted benzene derivatives, if two halogens are present, then in common naming system we use special prefixes like ortho, meta and para. Ortho is used to indicate positions 1 and 2. Meta is used to indicate positions 1 and 3. Para is used to indicate 1 and 4. Then this compound is called ortho, small o. Do not write capital. Ortho dichlorobenzene. Most of us do these silly mistakes, that is, while writing common names, if they are ortho, meta or para substituents, then the first letter should be a small letter only and never capital. Then write hyphen. What alphabet follows after the hyphen should also be a small letter. If you are writing ortho dichloro, this is wrong. If the first letter is a small letter, then the next letters should be small letters only. So ortho dichlorobenzene, and IUPAC name is 1,2 dichlorobenzene, 1,2 dichlorobenzene. Similarly, if for this example, you can write either alternate single and double bonds or a circle, both remain same. Common naming system, position 1 and 3 are called meta, so small m dash. Some of you also write this name as ortho dash dichlorobenzene. Writing this is not wrong, but it is not more appropriate way of naming any compound. If it is ortho, you are supposed to write only small o dash. If it is meta, small m dash. If it is para, small p dash. So meta dibromobenzene. Then IUPAC name will be 1,3 dash dibromobenzene. Let us see one more example. This time the positions are 1, 2, 3, 4. Para dichlorobenzene, para dichlorobenzene. IUPAC name will be 1,4 dichlorobenzene. For your syllabus, you have only di-substituted benzene derivatives nomenclature. If there are more than 3 substituents, such examples will not be asked in the exams. But for remembrance, I shall tell you, if there are 3 bromine, if there are 3 bromine attached to benzene at exactly symmetrical positions. Symmetrical position means one substituent, one gap, one substituent, one gap, again a substituent, one gap. If this is the case, then in common naming system it is called symmetrical, sim tribromobenzene. IUPAC rules remain same. You keep on numbering them and then write their positions 1, 3, 5 tribromobenzene. If there are more than 2 substituents in the benzene ring, then such examples will not be asked for naming in the exam. You can remember nomenclature only for up to di-substituted compounds. After nomenclature, we shall now see the nature of CX bond. We have studied in haloalkanes that the nature of CX bond, that is this bond, was a polarized bond. It was a polarized bond, hybridization being sp3. This bond in this CX bond, halogen carries partial negative, partial positive charge. Because of this reason, because of this halogen behaving as a nucleophile, nucleophilic substitution reactions were easier. Whereas in haloarenes, we have a benzene ring onto which halogen is attached. So we are studying about this bond. In haloarenes, this CX bond is much more stabler. It is much more stabler than the bond of haloalkanes. The reason is, here the carbon atom, it is sp2 hybridized. It is sp2 hybridized. A sp2 hybridized carbon is having more percentage of S character. For this reason, the CX bond of haloarenes is more stable and less reactive than CX bond of haloalkanes. Haloalkanes are more reactive, haloarenes are less reactive. Haloalkanes are more reactive due to the presence of sp3 hybridized CX bond. Haloarenes are less reactive due to the presence of sp2 hybridized CX bond. After this part, now we shall see their methods of preparation. The first method of preparation is by electrophilic substitution, by electrophilic substitution of aromatic compounds. Electrophilic substitution of aromatic compounds. The best example for any aromatic compound is benzene. So, if benzene is reacted with any halogen, let us consider chlorine. This takes place in the presence of a catalyst like FeCl3, ferric chloride, which acts as a catalyst or else a halogen carrier, provided the condition is dark. So, in dark conditions, aromatic hydrocarbon undergoes electrophilic substitution. Electrophilic substitution means you remove any electrophile from benzene. From benzene, the best electrophile is the hydrogens. Each carbon has one hydrogen in it. So, if you remove this H as H plus, in its place who comes? Cl plus. So, removing one hydrogen from here in the form of an electrophile, substituting it by chlorine. This is electrophilic substitution of benzene to give you chlorobenzene. You might have studied this reaction in your first year also, chlorination of benzene. In the same way, if you have toluene, if this is subjected to chlorination under same conditions, ferric chloride and ferric chloride as catalyst or halogen carrier, then you are likely to get two products, orthochlorotoluene and parachlorotoluene plus HCl. You may ask, sir, why benzene gives only one product, why toluene gives two products? So, you should be aware, in the first year you have studied the ortho-para-directing nature and meta-directing nature of any substituent. In benzene ring, if there is any substituent present, it decides where the incoming groups should go on the benzene ring. We call that as a directive influence of substituents or functional groups. So, according to that, methyl group is a ortho-para directing group. For that reason, you will get two products, ortho and para, in this para being the major product, ortho being the minor product. Sir, if carrying out one reaction gives these two products, how should I separate them? Both ortho and para isomers have a very large difference in their boiling points, so you can easily separate them. Understood? This was first method. By electrophilic substitution of aromatic hydrocarbons, you can prepare haloarenes. One example is when benzene is reacted with chlorine in the presence of ferric chloride as a catalyst or a halogen carrier in dark conditions, you will get chlorobenzene. If the same reaction is done with toluene, you are likely to get two products. The two products have a very large difference in their boiling points, so they can be separated easily. Now, this reaction is valid only for chloro and bromo products. You cannot prepare fluorobenzene by this method because of very high reactivity of fluorine. It is somewhat easier to prepare chloro and bromo products. Now, if you want to prepare iodobenzene, then what should be done? In place of FeCl3, you are supposed to use ferric iodide, FeI3. But the reaction gives you, I'll write a rough reaction. If benzene is reacted with iodine in the presence of FeI3, then you are supposed to get iodobenzene plus Hi. This is preferred reaction. We say expected reaction, but hydrogen iodide is a very strong reducing agent. A reducing agent is the one which reduces the formed product. So, because of hydrogen iodide, it makes the reaction proceed backward also. So, you will not get the product in the desired yield. Say you want to prepare it in 100% yield. As soon as these two are formed, these two will react together and gives you again the reactants. For this reason, in order to remove the reducing nature of hydrogen iodide, you are supposed to add any oxidizing agent like nitric acid or periodic acid in it. What is the role of nitric acid during iodination of benzene? It removes the hydrogen iodide formed during the reaction. What happens if hydrogen iodide is not removed during the reaction? Hydrogen iodide is a very strong reducing agent. It reduces iodobenzene back into benzene. To avoid this reaction, name any oxidizing agent that can be added. It should be nitric acid or iodic acid or periodic acid, HiO4. This was first method. The second method. Second method is more popular method, famous method, and an important method from exam point of view. This question appears multiple times. So the second method is by Sandmeyer's reaction. Sandmeyer's reaction. Because it is a named reaction, this reaction is important for exam. How is this prepared? Whenever benzene diazonium chloride, benzene diazonium chloride, if it is reacted with cuprous chloride, along with HCl. If benzene diazonium chloride is reacted with cuprous chloride and HCl, then you will get chlorobenzene along with nitrogen gas. So this chlorine gets attached, nitrogen goes away. This reaction is called Sandmeyer's reaction. The same can be done for bromination. Instead of cuprous chloride, you are supposed to use cuprous bromide. Easy reaction. So Sandmeyer's reaction is valid for preparing chloro and bromo products only. Sandmeyer's reaction is valid only for preparing chloro and bromo products only. This is first thing that you have to remember. What is Sandmeyer's reaction? Whenever benzene diazonium chloride is reacted with cuprous chloride in HCl, chlorobenzene is formed. This reaction is called Sandmeyer's reaction. The same can be told for preparation of bromobenzene also. Can you prepare other compounds, I mean iodobenzene and fluorobenzene by this method? No, you cannot prepare. Somehow the other method is, if you want to prepare iodobenzene, then benzene diazonium chloride is simply shaken with potassium iodide. Benzene diazonium chloride is simply shaken with potassium iodide. You will get iodobenzene plus KCl plus nitrogen. But this reaction is not Sandmeyer's reaction. Sandmeyer's reaction is valid only for preparing chlorobenzene and bromobenzene. If somehow you want to prepare iodobenzene utilizing benzene diazonium chloride, then this benzene diazonium chloride salt should be shaken with solution of potassium iodide, which will give you iodobenzene. But formation of iodobenzene from benzene diazonium chloride is not Sandmeyer's reaction. If you make slight changes in the reactions, like the same benzene diazonium chloride is taken, instead of cuprous chloride or cuprous bromide, you use copper powder. If you use copper powder in presence of HCl, then also you are likely to get the same product. You will get chlorobenzene plus nitrogen. This reaction is also not Sandmeyer's reaction. What have you changed? You have changed only the reagents. Instead of cuprous chloride in HCl, you are now using copper powder in HCl. This reaction will also give you the desired haloarine, but this reaction is not Sandmeyer's reaction. It is called Gattermann's reaction. This is also an important question for exam. One is Sandmeyer's, the other is Gattermann. How are these two reactions different from each other? If benzene diazonium chloride is reacted with cuprous chloride or cuprous bromide with corresponding hydrogen halide, haloarine, that is chlorobenzene or bromobenzene is obtained, this reaction is Sandmeyer's reaction. Can you prepare iodobenzene by Sandmeyer's reaction? No, you cannot prepare iodobenzene by Sandmeyer's reaction. How can you prepare iodobenzene then? Benzene diazonium chloride is shaken with potassium iodide, it will give you iodobenzene, but this reaction is not Sandmeyer's reaction. Instead of cuprous chloride and cuprous bromide, if you use copper powder in presence of HCl or copper powder in presence of HBr, then you will get chlorobenzene or bromobenzene. This reaction is called Gattermann's reaction, or else. Again some small slight change. If benzene diazonium chloride is reacted with fluoroboric acid, HbF4, is called fluoroboric acid. Now you guess what likely product is to be formed. You have prepared iodobenzene, you have prepared chlorobenzene, bromobenzene. What other halogen is remained? Fluorine. So you can prepare even fluorobenzene by this method. The formed product is fluorobenzene plus nitrogen plus HCl plus boron trifluoride. What is this reaction called? This reaction is called Bals-Schiemann reaction. Bals-Schiemann reaction. Some books tend to give only the second name. This reaction is called only Schiemann reaction. Some books specify the first name also, Bals-Schiemann reaction. So whichever name is given, you are not supposed to get confused. So you today studied three named reactions. One is Sandmeyer's reaction, the second Gattermann reaction, third Schiemann reaction. Always remember the difference between the three reactions. In all the three reactions, the main reactant remains the same. It is benzene diazonium chloride. Along with this, if it is cuprous chloride or cuprous bromide in HCl, the reaction is Sandmeyer's. If it is copper powder and HCl or HBr, then it is Gattermann's reaction. If it is benzene diazonium chloride along with fluoroboric acid, the reaction is Schiemann reaction or Bals-Schiemann reaction. So you can prepare fluorobenzene by Bals-Schiemann reaction. You cannot prepare iodobenzene by Sandmeyer's reaction. Sandmeyer's reaction is valid only for preparing chlorobenzene and bromobenzene. These were the only two methods of preparation for haloarenes. Next we shall see their chemical properties. There are no physical properties to be studied. Directly we shall study the chemical properties of haloarenes. Under chemical properties, the main chemical property that we shall study is their nucleophilic substitution reactions. Their nucleophilic substitution reactions. I did tell you that in haloalkanes, CX bond is sp3 hybridized, whereas in haloarenes it is sp2 hybridized. So for this reason, haloarenes are less reactive. Many a times this question is asked in the form of give reason why haloarenes are less reactive towards nucleophilic substitution reactions. I mean to say, haloarenes easily do not undergo nucleophilic substitution reactions. Why don't they easily undergo nucleophilic substitution reactions whereas haloalkanes easily undergo? There are four reasons. The first reason is difference in the hybridization of carbon atom. Difference in hybridization of carbon atom. Let us study this one. In haloalkanes and in haloarenes, the CX bond is sp3 hybridized. The carbon atom is sp3 hybridized. Here it is sp2 hybridized. Halogen is attached to a carbon which is sp2 hybridized in haloarenes. So the percentage of S character in sp3 hybridization is 25% S character. In sp2, S character is 33%, 33.3%. Always remember, greater the percentage of S character, more will be the electronegativity of that atom. I mean to say, this carbon atom to which halogen is attached, it is sp2 hybridized. Its electronegativity will be higher when compared to the CX bond of haloalkanes. Greater the percentage of S character, more is the electronegativity of the atom. Greater the electronegativity, stronger is the pull of the electrons. This means the electrons present on halogens, they are tightly held by carbon in haloarenes. As a result, this bond becomes shorter. When carbon pulls the electrons from halogens because of the virtue of its higher electronegativity, because of sp2 hybridization, the electrons present on halogens are not given for donation, they are pulled away. Its density is pulled away by carbon. As a result, the bond becomes weaker or stronger. It becomes more stronger bond. Whereas in haloalkenes, the CX bond, the C or carbon is 25% S character, is having only 25% S character. Therefore, on comparative grounds, this bond is longer. Here the bond is shorter. Longer the bond, easier it is to break. Shorter the bond, difficult it is to break. Which one has a stronger bond? Haloarenes has a stronger CX bond because of sp2 hybridization, because of more percentage of S character. Because of more percentage of S character, greater electronegativity. Greater electronegativity means greater pull of electrons. Greater pull of electrons means shorter the bond. Shorter the bond means stronger is the bond. Stronger the bond means difficult it is to break. Difficult it is to undergo any reaction. For this reason, if halogen cannot break away from the bonds of carbon, if it cannot go away as a nucleophile, then the incoming nucleophile cannot attack this carbon easily. It cannot attack the carbon easily. For this one reason, haloarenes are less reactive towards nucleophilic substitution reactions because of sp2 hybridized nature of the carbon atom to which halogen is attached. The second reason is resonance. Can you write resonance structures for haloalkanes? No. To write resonance structures, you need alternate multiple bonds, single, double, single, triple. You need such bonds compulsorily for writing resonance structures. Such resonance structures cannot be written for haloalkanes. Can they be done for haloarenes? We shall see. Consider the example of chlorobenzene. If electrons from chlorine are donated to benzene, if this carbon atom takes away the electrons of chlorine, carbon can tolerate a maximum of 4 bonds. It can have only 4 bonds because its valency is 4. Now, it already has 4 bonds, 1, 2, 3, and this a pair of electrons also is counted as 4th. So, there are already filled valencies. Now, if extra pair of electrons approaches, then the electron density on this carbon increases. To reduce the electron density on this carbon shifts its own electrons to adjacent carbon. Then what will be the next structure? This bond remains intact, this also remains as it is. Here Cl, even if I do not write these dots, no difference will it make. So chlorine has lost its electrons, so it will carry positive charge. Understood? Since the electrons present here shifted between chlorine and carbon, this will become a double bond. Now this carbon lost its electrons to the adjacent carbon, it remains here as a negative charge. Negative charge cannot remain idle, so it keeps on shifting. This negative charge or a pair of electrons shifts here, electron density on carbon again increases, so it pushes its electrons to the next carbon. Then the next structure is this minus charge shifted here, means a bond is formed. This bond came out in the form of a negative charge. Again this negative charge shifts here, this double bond comes outside. Then the next structure will be, next resonance structure will be, here bond got inside, this bond came outside in the form of minus charge. Lastly negative charge here, again this bond shifts away, to neutralize the positive charge. You have the final structure as, this is your final structure, which is same as the first structure. So this continuous delocalization or shifting of electrons keeps on taking place in chlorobenzene. This kind of resonance structures cannot be written for haloalkanes. Sir, how is resonance useful to study whether a given compound is easily undergoing nucleophilic substitution, whether a given compound is favorable for nucleophilic substitution or not? Now you see, for writing resonance structures, here chlorobenzene, in chlorobenzene, this carbon utilized the electrons of chlorine. It utilized the electrons of chlorine. As a result, in the resonance structures, you will notice that this CX bond became a double bond. It became a double bond momentarily. So this double bond, when compared to a single bond, is a shorter bond. When bond multiplicity increases, when bond order increases, you have studied this in chemical bonding in the first year. When bond order increases, bond length decreases. When bond multiplicity increases, bond multiplicity means the number of bonds between two atoms. If the bond multiplicity increases, then also bond length decreases. When bond length decreases, it indirectly implies that that bond cannot be broken easily. If it cannot be broken easily, means it is less reactive. It is less reactive, therefore it cannot undergo nucleophilic substitution reactions. There are two reasons now that you have studied. One was difference in the hybridization of carbon atom. Because of sp2 hybridization, percentage of S character is more. For this reason, it will have greater electronegativity. Therefore, the electrons of halogen are tightly held by the carbon atom, making this bond shorter. To prove this point, we gave you another proof of resonance. From this also, you are now clear that because of resonance structures, the CX bond becomes a double bond. Double bonds are shorter bonds which cannot be broken easily. The third reason is instability of phenyl cation. It is instability of phenyl cation. What is instability of phenyl cation? Now say you can theoretically guess, if chlorobenzene is dissociated, you will get benzene plus chlorine. Chlorine carries negative charge, benzene carries positive charge. Theoretically, we can assume anything, but this is wrong. It does not take place. You cannot get benzene carbocation so easily. Benzene carbocation is called phenyl cation. So, if somehow by using any method you got even a phenyl cation, if by any method you got this reaction, you are able to generate this phenyl cation, it is highly unstable. It is highly unstable because it is not stabilized by resonance. You cannot write resonance structures for a phenyl carbocation. For phenyl carbocation, you cannot write resonance structures. Because of its instability, this reaction is not favorable. Sir, why phenyl cation comes into picture? A nucleophile easily attacks that place where there are no electrons. So you can guess, sir, it is already carrying positive charge. No, sir. If it is carrying positive charge, means it is deficient in electrons. If it is deficient in electrons, the incoming nucleophile which carries negative charge, it can attack easily. To attack, it should have a plus charge on it. But generating a carbocation itself is an arduous task. It's a very difficult task. For this reason, because phenyl cation is highly unstable, it cannot be generated so easily for getting attacked by a nucleophile. Haloarenes cannot undergo nucleophilic substitution reactions. The last reason is high electron density. High electron density. Now you might have noticed in the resonance structures that benzene already has 6 electrons. Where are 6 electrons? 1, 2, 3, 4, 5, 6. There are 6 delocalized electrons. There are 6 delocalized electrons belonging to whom? Belonging to benzene. So even if chlorine is not attached, even if Cl is not attached to benzene, benzene already has surplus electrons. It has 6 electrons which keep on rotating on all the carbon atoms. Now along with these 6 electrons, now chlorine is also donating a pair of electrons. Chlorine is also donating a pair of electrons. So electron density on benzene, I mean to say the overall haloarine, the electron density on benzene ring increases. Electron density increases means negative charge increases. Whenever there is a negative charge on the overall molecule, assuming so, if there is negative charge, then you have a nucleophile which wants to attack here. Negative charge and negative charge means their electron clouds will repel each other. Because both carry the same charges, the incoming nucleophile cannot attack benzene ring because of high electron density. The electron cloud of benzene ring as well as the electron cloud of the nucleophile both will repel each other, making it difficult to undergo nucleophilic substitution reactions. Therefore, because of these 4 reasons, haloarenes are less reactive towards nucleophilic substitution reactions compared to haloalkanes. So if in the exam they ask you, give reason why haloarenes are less reactive towards nucleophilic substitution reactions, what should be your answers? Your answers should be 1. It is due to the difference in the hybridization of carbon atom. Haloarenes have sp2 hybridized carbon atom to which halogen is attached. Because it is sp2 hybridized carbon, the percentage of S character is high. Because of high percentage of S character, the electronegativity of that atom is higher, making the bond shorter, making the carbon to pull the electrons of halogens towards itself, making the bond shorter. A shorter bond is less susceptible for getting attacked by a nucleophile. The second reason is resonance. Since haloarenes undergo a number of resonating structures wherein the benzene becomes electron rich center and the carbon halogen bond becomes a double bond. It acquires partial double bond character. Because of this partial double bond character, the bond becomes a shorter, which cannot be attacked easily by an incoming nucleophile. The third reason is instability of phenyl cation. For a nucleophile to attack any center, the center should be having deficiency in electrons. This can happen only when benzene carries positive charge. For benzene to carry positive charge, halogen should leave the benzene. This cannot happen because benzene carbocation or phenyl carbocation is highly unstable. It cannot be generated. Since it cannot be generated so easily, the nucleophile cannot attack the benzene ring. Therefore, haloarenes are less reactive. And the final last reason is high electron density. Benzene has 6 delocalized electrons. Along with it, the halogen attached to it also donates its electrons. Due to this surplus extra more number of electrons, benzene on the whole becomes a electron rich center which cannot be attacked by a nucleophile because benzene is also carrying negative charge. The incoming nucleophile also carries negative charge. Both the negative charges, their electron clouds repel one another, making it difficult or less available for getting attacked by a nucleophile. These are the 4 reasons why haloarenes are less reactive compared to haloalkanes in terms of nucleophilic substitution reactions. Now in the next class, we shall study some of the nucleophilic substitution reactions and the specified conditions required for them. Along with the nucleophilic substitution reactions, we shall study some other electrophilic substitution reactions also. Thank you.